Okay, here we are in Lagrange with particles. Remember, this is the primary dynamics method as opposed to a vector approach, Newton-Euler approach. And to get to Lagrange, there was this process. First, we had virtual work. Then we had the idea of generalized coordinates. And the idea of the generalized coordinates is we could write R as a function of the Q sub I for I equal 1 to N. And so the virtual R is given as the partial of R with respect to each of the Q's. And now we're summing over J equal 1 to little n times the virtual Qj. So we can replace our vector description R with a description in terms of these generalized coordinates. So we have to write R in terms of these other coordinate things. And they could be coordinate directions. That's the typical thing you do, but they could be anything. The third building block, now virtual work, though, left us with in a static sense only. Notice there's no dynamics here, statics only. We could write static equilibrium, which is that the virtual work for a system in equilibrium has to equal 0. And that gave us a formulation. But the third building block was D'Alembert's principle. And D'Alembert's principle replaced added another force called an inertial force into the system. When you take D'Alembert's idea and plug it into virtual work, you get the generalized principle of D'Alembert. And the idea there was that we had this sum of the F sub I dotted with the partial of R sub I plus a minus M sub Ri double dot dotted with the virtual R sub I for I equal 1 to cap N. And if we did that over all the particles, that would have to equal 0. So that was D'Alembert's principle. We added this part. And then fourth, we moved to Lagrange. And recall the idea with Lagrange. The idea with Lagrange, he took this first thing and called it a Q sub J, which was the sum, the Q sub J was the sum of the F sub I dotted with the partial of R sub I with respect to Q sub J. That's I equal 1 to cap N particles. And then he replaced this thing. This was the crazy part they came up with, but he replaced this all in terms of an energy function, this T. And so we said it was the partial of T with respect to Qj dot. We take the ddt of that, and we subtract the partial of T with respect to Qj. So he replaced these two elements as follows. When we did that, we wrote Lagrange in the following way. The ddt of the partial of T with respect to Qj minus the partial of T with respect to, that's Qj dot, sorry, minus partial of T with respect to Qj equals this cap Qj. And over here, there's a sum for J equal 1 to little n. So you have to sum over all the particles. But, and we dot that with the variation in Q sub J. But the idea is if the Q sub J's are independent, then it must apply to each. So to each coordinate, to each coordinate Q sub J. That's the idea here. So I would get, that gives n such equations. Let me say that one more time. This gives n such equations, you know, one for each qj, and I'll use those to solve for my unknowns, and the unknowns will be its dynamics, and the unknowns will be, let me write that down, used to solve for the unknowns, and I'll ask the question, and the unknowns are, and I'm pausing for a moment. Feel free to answer if you like. And the unknowns are the Q sub j double dots for j equal 1 to little n. Over here, I'm going to recap one more time. So we have n particles, and we have little n coordinates. So that's Lagrange's method. I want to add one other thing. If you have questions, please jump in here. I want to add one other thing to Lagrange. So, by the way we write Lagrange then is going to be the ddt of the partial of t with respect to qj dot minus the partial of t with respect to qj equals cap qj. That's how we write it. So we just write it for each. We assume that these q sub j are independent. That's the assumption. That's how we write Lagrange. And I guess I need also for a recap to remind you what T is. T is the kinetic energy. So I have to sum over all the particles, I equal 1 to cap n. And this is the m sub I, r sub I vector dot, dotted with r sub I vector dot. So it's 1/2 mass times velocity squared. All right, now there's one other addition I want to make to this, and then we'll jump into examples. Actually, change my mind. Time to do an example. And listen, Lagrange is very powerful. It's an alternative method to Newton-Euler. Same result. You don't get any different result than you get with Newton-Euler. It's just an alternative approach. There are advantages and disadvantages. We will start with we're going to start with some simple examples. Don't let that fool you to think that I could apply Lagrange to any problem. I could apply Newton-Euler to any problem. It's really my choice. Okay, so the first one, again, is going to be very simple. It's going to be a pendulum. It won't take us long to work through this problem. And in this problem, I'm going to define my inertial frame. A little odd. I'm going to make my N1 be down, my N2 be to the right. I'll have some angle theta. I'll attach a frame to the body. So I'll call that my B1 and my B2. Let this be length L and that be mass N. And I want to solve the equations of motion. So how do I go about doing it with Lagrange? Well, first, let me compare and contrast. If I was doing Newton-Euler, I would have to write the kinematics, but I would create a free body diagram, get the forces, sum the forces in all the directions, write the equations of motion. With Lagrange, I need to solve kinematics along the way, but with Lagrange, I go to energy. So the first thing I do is write my energy. So I'm going to write energy for the system. And in this case, you know, we're doing particles, so it's system particles. So we're going to sum over I equal 1 to cap n, which is equal 1. There's one particle. And the energy is going to be 1/2 times the mass times the velocity, which we'll call r vector dot, dotted with r vector dot, r squared, r dot, dotted with r dot. So I need r dot, so which we've been calling v of my particle. So v, which is, you know, r vector dot, which is the ddt of r. I need that. So the ddt of r, I'll call that L in the b1 direction. When I take the derivative, oops. When I take the derivative, the first term is the ddt of L b1 in the b1 frame, which is 0, plus the angular velocity of b with respect to n crossed with lb1. So that tells me I need to get the other parts of my kinematics. The other parts are going to be, well, I may need it. So let's write down, I'm going to get a rotation from b to n, which is a rotation around the 3-axis by theta. So it's a c theta, negative s theta 0, s theta, c theta 0, 0, 0, 1. The angular velocity of b with respect to n is theta dot around the b3 direction. I can now plug that in. When I plug this into my equation, I get a 3 cross a 1, gives me a positive 2, so I get a positive theta dot L in the b2 direction. I can now carry this velocity back to my energy. This is my kinetic energy. So T is 1/2 mass theta dot L in the B2 dotted with theta dot L in the B2, which is 1/2 m theta dot, let's say L squared theta dot squared. Okay, so the first step is to get the energy of the system. And along the way, you'll have to do the kinematics to do that. Second step, I now am ready to get the components. You know, let me back up. Allow me to have a 0 step. So step 0, we're going to list our generalized coordinates. We're going to list Q, oops, our generalized coordinate vector. And in this case, you know, I could choose any set of coordinates to describe my mass, but I'm going to let Q equal my theta. My bad for not saying that right off the bat, but I'm adding it in afterward. It would make sense to think about that right up front. Note that this is a 1 degree of freedom system, so I've got one generalized coordinate. I could use other generalized coordinates. This one seems obvious. What else could I use? I could use X. I could use Y. I could use something that I could use something else. At this point, though, let's just agree we'll use theta. All right, so I need to go through the components of Lagrange. So Q1 equals theta, which is all the Q's that I have. So I first need the partial of T with respect to Q1, which is the partial of T with respect to theta, which is the partial of, well, let's just look at it. The partial of T with respect to theta, there isn't a theta in T, so that's just 0. Next, I need the partial of T with respect to Q1 dot, which is the partial of T with respect to theta dot. I do have a theta dot in T, So it's 1/2 ml squared times the ddt of theta dot squared. So that's going to be 2 times 1/2 ml squared theta dot. And then finally, I need the ddt of the partial of t with respect to q1 dot, which of course is the ddt of the partial of t with respect to theta dot. So I need to take the ddt of this thing. So m is a constant in time, L is a constant in time, theta dot is a variable in time, so that gives me ml squared theta double dot. Next, I need, so those are some of the components of Lagrange, and then I need I need the generalized force, cap Q sub j. Cap Q sub j, I have to sum over all the particles. Again, that's just from I equal 1 to n equal 1 to 1. N is 1. And I need all the forces acting on that particle dotted with so I need the forces acting on it dotted with the partial of my R of that particle with respect to my Q J, which in this case is my Q1, which is theta. So it's respect to Q theta. So my forces, you know, I said you don't need a free body diagram, but I guess we do need to write out the forces. If we think about the forces, I'm going to have a tensile force in the negative B1 direction, and I get gravity going down in the N1 direction. So that's going to be a negative T in the B1 plus an mg in the N1. I'm going to pre-multiply this guy by a projection from B to the N frame transpose. When I do this, I can rewrite this as negative T in the B1. Peek up, think in my head here. That's going to be an mg cos theta in the B1 minus mg sine theta in the B2. I think I've got that correct. So that gives me mg cos theta minus t in the B1 minus mg cos theta in the B2. All right, the next thing I need is the partial of r sub I with respect to q sub j, which is theta. And we said that r sub I was L in the B1 direction. Yeah. Now, when I look at this term, let me make 2 comments. Well, the 2 comments are there are 2 directions to go. There are 2 approaches. The first approach, mg sine theta, yes, thanks. You guys are correcting my errors and taking notes. So I'm going to give you a break there to catch up. Sorry. There was an error you guys just pointed out. Okay, there's 2 approaches to taking the partial of this r with respect to theta, because we need it to dot to get the generalized force. In one approach, I'm going to, take the derivative as shown, okay? So one is as shown. The second is to use the cancellation of dots. you know, that little cancellation of dots thing that I told you, which was the partial of r sub I with respect to qj equals the partial of ri dot with respect to qj dot. This one is much preferred, and that's the one I'm going to use, but I do want to mention in the former method, you can still take the derivative. You just have to remember the idea of the transport theorem. So I'm taking the partial with respect to theta, but right now this guy is written in the body fixed frame. So I would either have to cast that back to the inertial frame, take the partial with respect to theta, and then put it back, or I could use the transport theorem. So the first method, taking it as shown, you know, either put it in the N frame, take the derivatives, put it back in the B frame, or use the transport theorem. It also applies here. If I use the cancellation of dots, that one's going to be that one's preferred and a lot easier. If I do that one, it will be, I'll need the partial, the velocity was, what, ml theta dot with respect to theta dot, and that's just m times L. Oops, there's no m. It was just L theta dot. So it's L. And by the way, I forgot something. It was L theta dot in the B2 direction. When I take the partial with respect to theta dot, it just gives me LB2. Okay, when we go put that back into our Q sub j, that means I'm going to get mg cos theta minus t in the B1 minus mg sine theta, got it right this time, B2, that's my force, dotted with my partial of r with respect to qj, that's LB2. That will give me minus mg ls theta. So step 2, the components of my Lagrange are now known. I did this for Q1. I would have to do it for Q2, Q3, all the way up to Qn. In this case, there's only one Q, you know, only one term in a generalized coordinate. So I'm done. I stop there. Step 3, I assemble Lagrange. I assemble Lagrange's equations. So it was the ddt of the partial of t with respect to theta dot, ml, so that's my ml squared theta double dot, minus the partial of t with respect to theta, that was 0, equals cap q sub j, that's minus mg ls theta. I pull the whole thing together, I get ml squared theta double dot plus mg ls sine theta equals 0. I can, of course, cancel out the m and the l, but that's the pendulum equation we know and love. We could have just rattled that off using Newton's method or the like, but it was a simple example, showed us how to do Lagrange, all right? And I want you to note a couple things. Note there was one generalized coordinate that gave us one equation of motion. The constraint forces, remember the constraint forces do no work, so the constraint forces don't show up. So I end up directly with equations of motion only. In other words, no algebraic constraints. Okay, very simple example, but that's Lagrange. Now, I want to jump back in. Let me give you a second to catch up on that, and then we're going to jump back in and finish a point that I want to make on Lagrange. So I assume everyone's ready to move back forward. So now let's go consider a special type of force. And this is in Lagrange. And this special type of force we're going to call a conservative force. All right. What's the idea of a conservative force? Well, it's one that's conserved. What does that mean? It means, I guess we could say it in a couple different ways. A conservative force means that if I apply, if I'm moving over a path from A to B, I get some force. If I've moved back to A, what happens? The work done in going from A to B and then back to A has to equal 0 if it's conservative. All right, that's what that means. Another way of saying it would be that the force depends on displacement only. So in other words, our force is a function of R, not a function of R, maybe R dot time, other terms, but it's a function of R only. Or our Q's, if you will, prefer Q's. All right, so for the conservative force, it can then be shown that for a conservative force, and I'm going to put here in parentheses, it can be shown, meaning somebody showed it, and right now we're just going to take them at their word. This is well accepted that the force is defined by definition here as the negative gradient of a scalar function, okay? So by definition, F vector is this thing. Let me talk about these three terms. There's three terms here. There's a negative, there's this cap del, and then there's this V. The negative is just a negative sign. Comes from the derivation. I, in the past, have forgotten the negative sign or gotten confused by it. I just remind myself it's part of the derivation. You can show it. One way to do it is Meyerowitz shows it by doing a boundary integral and then applying Stokes' theorem. It just falls out of Stokes' theorem, but except that there's a negative sign. So if you have a conservative force, you've got a conservative force from a scalar, you get the negative sign. This cap del, that's the gradient operator. And it takes the partials in all directions. It takes the gradient in all directions, sometimes called grad. It takes the gradients in all directions, much like a Jacobian. Some would say it's the same. I would kind of consider it the same, but there are some small nuances. We'll just say it's much like the Jacobian. And finally, V is a scalar function. And we're going to see, I mean, the scalar function that I always use in dynamics is the potential energy. Now, I suppose there are situations where it could be something else, more generically from a mathematical standpoint. But I think really in mechanics and dynamics, we're going to see that a conservative force can be pulled directly from the potential energy through this operation here. All right, so if we have this guy, so this, we're going to accept this from now on by definition. So if we have a potential energy, it's a scalar. If we take the negative gradient of that scalar, we can get the equivalent the equivalent resulting force. And that's by definition. So if we plug that into our Q sub j, then we said, you know, it's the sum for I equal 1 to kappa n. We'll ignore that at the moment. So it's going to be this F sub I dotted with the partial of R sub I with respect to Qj, which is now negative del V dotted with the partial of my R sub I with respect to Qj. And this is the, I guess, the potential energy associated with particle I. The gradient, the gradient of my V is the partial of V with respect to X plus the partial of V with respect to my Y plus the partial of V with respect to Zi. And, you know, that's that term. My partial of R with respect to my Q is going to be, you know, again, the partial of, it's going to be the partial of my R sub X, or I'll just call it at this point my partial of X with respect to Q J plus the partial of Y with respect to Q, this is my QJ, plus the partial of Z with respect to QJ. If I dot these two, I see that I simply get the partial of V with respect to Q is the partial of V with respect to X dotted with, or times, the partial of X with respect to Q plus the partial of V with respect to Y dotted or times the partial of Y with respect to Q plus the partial of V with respect to Z dotted with the partial of Y with respect to Q. And I can see that that's exactly what I get up here with the Q sub J, barring the minus sign. So I can see that cap Q sub J equals negative del V del Q J. And I'm being a little sloppy with my J's. I'm looking at this one generalized coordinate at a time, hence I get a Q sub J. I'll give you a second to write that down and then I'll recap. Okay, so to recap, for a special class of forces, a conservative force, which by definition, conservative force is going to be defined as negative gradient operator acting on a scalar function, which for us is potential energy. If I plug that back into my generalized force, I can see that the generalized force resulting from a conservative force is given directly as the negative partial of V with respect to Qj. If I put that back into Lagrange, and that should probably be a capital L, then I can rewrite Lagrange this way. The ddt of the partial of t with respect to Q sub j dot, that's the first term, minus the partial of t with respect to Qj. Then look, on the right-hand side, I had that Qj, but I'm going to pull out the conservative forces. So I'll make this star. Those are that's the generalized force for non-conservative forces. Okay, so that's the Q sub j I would get after I've pulled out the conservative forces. And then I get this Q sub j that I just calculated, which is negative partial of V with respect to Qj. I'll move to the right-hand side, so I get plus partial of V with respect to Qj. So I get this thing. And this is probably the way that everyone looks at Lagrange. This is the way that everyone looks at it. As a matter of fact, usually we drop the star, and we just assume that QJ are the non-conservative forces. You don't want to double count the forces. You don't want to double count them in potential and in the force on the right-hand side. And then there is one other way that we can look at Lagrange. Okay, so here this Q sub J is the non-conservative forces. I guess we've said that. So there is one other way we can look at Lagrange. And not look at it, but it's written. And that is to define a thing called the Lagrangian. Wow, what a neat thing. Rewrite analytical dynamics and get a Lagrangian named after you. That is really exciting. The Lagrangian, L, is this sum of the energies, but it's written as T minus V, okay? So T is the kinetic energy, V is the potential energy. If you do this, and you'll note that V, we said a conservative force is a function of Q's only. So if I take the partial of potential with respect to Q dot, it'll be 0. So I can rewrite Lagrange one more time, and this is the way I like to write it, which is the ddt of the partial now of the Lagrangian with respect to Qj dot minus the partial of Lagrangian with respect to Qj equals cap Qj. Probably this is the way you see Lagrange's equations written. The Lagrangian consists of the kinetic minus the potential. You have the difference in those. You can see by comparing the partial of V with respect to Qj dot is just 0. So the first term is just the same. The second term, I get the minus the partial of T with respect to Qj. Third term, I get a minus, so it gets a plus partial of V with respect to Qj. So they're equivalent. And then the right-hand side stays unchanged. I drop the Q star here just to imply that this Qj consists of the non-conservative forces. So this is Lagrange. This applies to any system you can think of. In our case, we're set up for particles, although, frankly, this form is written in any case. What'll happen is when we get away from particles to rigid bodies, I'll redefine kinetic and potential energy for you. And same with the QJ. It applies to any system particles. And at the moment, it deals with holonomic constraints only. Okay. I'm gonna let you guys do that. Michael lost his phone connection. Anyone know how to get it back? I guess. For the delete. Okay. So that's Lagrange's equation for particles. All right, we're moving along here. I've done one example. Now it's the time to learn about Lagrange the real way, and that's by doing examples. So let's see if we can burn through two examples here. I'm looking at the examples I have. I've got a bunch of them. Let's try to work through two. Well, yeah, let's see what we can do. The whole idea, one thing I like about Lagrange is it's fast. You have to write the velocity, but once you've done that, everything it's just first derivatives, and it goes pretty quickly, and you get right down to the simple system. So let's look at our examples. Okay, let's go back to the pendulum again. So we had the pendulum, mass L. And let's revisit the pendulum now and look at this force, this conservative force. So I'm not going to reconstruct everything, but I think this is the primary thing. So we had B1, B2, our step 0, I'm going to try to remember to do that from now on. Q was just theta, or vector Q was just this theta. Step 1, we needed to get the energies. So now I need T. So T is going to be 1/2 m v dotted with v. And we said that the v was, what did we say? It was L theta dot in the B2. So that makes the T be 1/2 m L squared theta dot squared. And by the way, that v is a vector. A little confusing. My v and my potential look the same. My potential v is my potential energy. So how are we going to do our potential energy? So the way we do a potential energy is you just need a datum, a reference. And in this case, I'm going to let my reference here be the N2 axis. So my energy is going to be equal to 0 there. So my energy at any point in time is just the displacement really in the N1 direction. So it's going to be mg times the height in the M1, which in this case is negative L cos theta. So right now my energy is minus mg L cos theta. If I put in theta equal 90, my energy goes to 0. If theta is something slightly larger than 90, it goes positive. So that's my energies. Step 2, I need my components from Lagrange. So first I'm going to do J equal 1. Of course, there's only one of them. So my Qj equals my theta. So I get first the partial of t with respect to theta, that's 0. I get the partial of t with respect to theta dot. I've already done that. That's going to be 2 times 1/2 times ml squared theta dot. I'm going to get the d dt of the, can't even write my d's correctly. The d dt of the partial of t with respect to theta dot. That's the derivative of this, so it's ml squared theta double dot. And then finally, I need the partial of v, my cap v, with respect to theta. I take the derivative of this thing with respect to theta. That is a function of my q, so it is going to be a function of theta. So I get a minus times a minus plus mgl s theta. My cap q sub j is, the sum of the forces. So my force in this case is just going to be a negative t in the B1 dotted with the partial of my r with respect to q with respect to theta. Partial of r with respect to theta is equal to the partial of r dot with respect to theta dot, which is the partial of L theta dot in the B2 with respect to theta dot, which is L in the B2. I get L in the B2 dotted with negative T in the B1. That goes to 0, so my Qj equals 0. And finally, I can write down my Lagrange's equations. and it is ml squared theta double dot minus 0 plus mgls theta equals 0. This was my qj. This was my partial of v respect to qj. This was my partial of t with respect to qj. And this was my ddt, the partial of t with respect to qj dot. Okay, another questions? If you have a question or want me to slow or comment on that more, put a comment in the chat or call out. Okay, next example. Now let's go to something with a little more motion. Now I've got my very hypothetical bead on a hoop. Run into these all day long. So here's a little bead spinning on a hoop, or bead on a hoop. My hoop is spinning at some kappa mega. My bead is out here, free to spin with some little theta. I'll have some N1, N2 direction. Partway in, I'll have an A1 and an A2 direction where A is spinning relative to N by this kappa mega. And then finally, I'll get a B1 and a B2 attached to the bead. My writing's getting a little small there, I apologize. Hopefully you can see that. I'll try to make those a little larger. We'll call the radius of the hoop R and the mass of the bead M. So step 0, I need to get my generalized coordinate set. What's it going to be? Well, let's see. It looks like I've got, I can spend some time working through and thinking about the options. These examples, I've got them set up. They're already I've kind of chosen them. So maybe at the moment, let's move through these quickly because I'm trying to show just some basic practice points. You could say, though, that, look, I've got kind of two obvious angles, kappa mega and theta. But in this case, I'm going to let my kappa mega be a constant rotation. So since it's a constant, it's really not a coordinate per se, right? It's a constant. So I'm going to pull it out, and that'll just let my generalized coordinates be theta. So it's a 1 degree of freedom system, 1 generalized coordinate. Step 1, I need energy. To do that, I need the, I need my velocity, right? 1/2 v dotted with v. So I need to work my way through my velocity. First, I'm going to get my r, my displacement. You'll notice I could start anywhere. Let's say I start up here. Call that h. So it's like it's a negative h in the A2 direction. And then it's a minus r in the B2 direction. I need to get my velocity. With my velocity, I'll take the derivative of this thing. I'll see that the derivative of this guy all goes to 0. H is not moving. That point's not moving. It's constant. And then I'll get a, for this guy, I'm going to get first a 0 in the B frame. plus my angular velocity of b with respect to n crossed with negative RB2. I need the angular velocity of b with respect to n. The angular velocity of b with respect to n is going to be two components. It's going to be kappa mega around my A2 plus a theta dot around my B3 direction. I need to cast this A into the B frame. So I need to pre-multiply this guy by a rotation from B to A transpose. And the rotation from B to A, that's a rotation around the 3. So it's going to be a cos theta, sine theta 0, negative sine theta, cos theta 0, 0, 0, 1 times 0 kappa omega 0. It's an A-frame, plus 0, 0 theta dot. I'll rewrite this again. That's going to be sine theta kappa omega in the B1 plus cos theta kappa omega B2 plus theta dot in the B3. Now I have to cross, now I'm ready to go back to V. V is going to be this thing crossed with that guy. So I get a 1 cross a 2 gives me a 1 cross a 2 gives me a positive 3. So I get a positive negative R sine theta kappa omega in the B3. I get a 2 cross a 2, that's 0. I get a 3 cross a 2, that's a negative 1. So it looks like I'm going to get a positive R theta dot in the B1. So that's my velocity. My kinetic energy, T, is now going to be 1/2 m v dotted with v. So that'll be r squared theta dot squared plus r squared sine squared theta kappa omega squared. And then my potential energy, let's call this point here my energy reference. So right now everything below it is negative, everything above is positive, and below it I get a minus mg cos theta. Now I'm ready to go to step 2. I need the components of Lagrange. So first I have j equal 1. It's the only j I have. For j equal 1, q sub j equal theta. So I get the partial of t with respect to theta. I do have a partial of t with respect to theta in this case. So it looks like it gives me m r squared sine theta kappa omega. Let me rewrite it. M r squared kappa omega squared times 2 times the sine of theta, which I already have pulled out the 2, times cos theta. Okay, that's my first term. The second term is the partial of t with respect to theta dot. That is m r squared theta dot. The d dt of the partial t with respect to theta dot. Looks like it's m r squared theta double dot. And then finally, the partial of cap v with respect to theta is positive mg sine theta. Next, I come to my q sub theta. Q sub theta, here's really one of the big benefits of Lagrange. Let's think about the forces that we have. Well, we've got gravity acting on this bead, but that was conservative. We've accounted for it. On the hoop, we're going to get a force in the B2 direction, and we're going to get a force in the B3 direction, right? The hoop is going to provide those two constraints. One constraint, B2, keeps it moving in and out of the bead. The force in the B3 keeps it from moving in and out of the plane, as I'm seeing right here. But those are constraints, correct? Those constraints do no work. They're constraint forces. So when I go to write my generalized force, I only need to consider non-conservative but not constraint forces. Oh, okay. Okay. Got a little correction there. Yes. MGR cos theta. You guys are watching me. Thank you. This came from the chat line. I've missed an R in this potential function. Thank you. Mass times gravity times height. The height is R cos theta. Good. Thanks, guys. Back to the Q. So Q represents at this point the non-conservative forces, but constraint forces don't count because they're going to disappear. Now you could include the constraint forces. When in doubt, include them. You would find though in dotting with the variation in R that they're going to go to 0. All right. Finally, step 3, we can assemble Lagrange's equations, and there'll be just one. We get the ddt of the partial t with respect to theta dot, so we get m r squared theta double dot. We get minus the partial of t with respect to theta, so we get minus r squared kappa omega squared sine theta cos theta. We get plus the partial of v with respect to theta, that gives us plus mg r sine theta. That equals cap q sub j, which equals 0. And this is our equation of motion. That's a beautiful thing. We did that quickly. It gave us directly our equation of motion, no constraints in it. So no, that's the nice thing about Lagrange. Okay, great. We're on a roll here. I'm going to stop the recording. I don't know why I'm doing that, but let's stop the recording.